Oh my God.
Did you know the guy who made the comment? I had no idea. That's great. Was he the primary vendor? And what is he doing now?
He studies over the company.
Well, and actually, it's kind of, you feel a little bit neglected if you haven't been downside down.
Half of this room is probably sick of hearing from me already as the absorbent carbon workshop. The other half haven't heard from me yet, but probably will be sick at the end of this. Really, well, first of all, I should tell you that my name is Frank Derbyshire. I'm the director of the Centre for Applied Energy Research at the University of Kentucky, which is the organisation that has helped to put these workshops together. And I know Peter Eklund has done this in the nanotubes workshop this morning. At least I hope he has made various announcements and welcomed you. I'd like to do the same while we have one collective group together. And I think this will be the only opportunity, because this evening I presume we'll all be rat-arsed and dancing around and filling your faces with food and won't want to hear any more speeches at all. So I'd really just like to extend a welcome. I personally, from what I've seen so far, believe that this is the best of the workshops we've yet had. The numbers are down from the last one we had, which makes it much easier to deal with, better discussion, and I think we'll continue in this vein. If everybody's happy at the end of tomorrow evening, we'll look again at doing this in 2 years' time. Just to give you an idea, I just had someone do a tot-up, Teresa, I think, just of the attendees here. We have, between the two workshops, 79 people. I think an impressive ratio of academic and industry representatives, which are 57 and 22. And collectively, everyone is represented across 8 different countries. So I think that's quite commendable for a workshop of this size. Well, I won't continue. What I'd really like to do, apart from that collective greeting, enjoy yourselves. If there's anything we can do to really help your stay more enjoyable, of course there are boundaries in what some of us might be prepared to do to make it more enjoyable. But apart from that, I'd really like to hand this over to Peter Eklund now, who will introduce Dr. Smalley.
It's a pleasure to have Professor Richard Smalley from Rice University here for the workshop, and today he will tell us about the future of colorings. I'm sure that all of you are aware that Professor Smalley is the 1996 Nobel Prize winner in chemistry for the discovery of fullerenes. The prize was shared with Harold Proto and Robert Pearl. And not only was Professor Smalley associated with this rather dramatic discovery, but also a very short time ago, his group also made a rather dramatic discovery about the production of carbon nanotubes at rather high yield. And today, Professor Smalley will tell us about the road from, I suppose, 1985 to the present.
Thank you. I'm going to stay down here so that I can be expeditious in getting the overheads on the screen. We're probably up a little bit too high here. I do want to talk about the fullerenes, but from the viewpoint primarily of these new developments of nanotubes and of carbon more generally. Try to put this into context. the principal lesson that was learned in 1985 is that it is possible to make a molecule out of carbon without using any other element. And the older I get, the more I appreciate how cool it is to be a molecule. When I teach freshman chemistry, which I've been doing the past couple of years, I make a big point of how it ain't easy to be a molecule. It's not just that the atoms are held together by covalent bonds, but in addition to that, it is that once all the atoms that are going to be part of these molecules put together with their bonds is done, you have an entity which maintains its identity even when it nestles up against other entities of its sort, with other molecules, at least of its same sort, hopefully with other things as well. And in particular, in our world, it maintains its integrity even when exposed to water and oxygen. If it doesn't do that, its uses are highly restricted. Well, it turns out there is, as we now know, a way of making a pretty darn happy molecule just by wrapping the graphene sheet around on itself and pentagons to provide a positive curvature to give, well, in its most symmetrical form, this C60 structure, which I believe is hands down the most symmetrical possible molecule you can make in our universe. But it's also effectively a harbinger of what we now realize is an infinite class of molecular carbons, which can take all manner of structures in the three-dimensional world that we live in. I like this one in the shape of a Y. We like to call it a Y non-fullerene because we don't know why not. Why it would not be stable and be a perfectly happy, functional entity in our world with air and moisture around if we were only able to find some strategy of getting the atoms into that place. This object shares with all other fullerenes the property that it has divided space into two volumes, an inside and an outside, separated by a single atom layer that is effectively a membrane that under virtually any reasonable conditions is impermeable. Even though when we look at these structures, and everybody in this group is very used to looking at hexagonal structures, we see mostly the holes between the atoms, but in fact, as you well know, those holes really aren't very big at all. In fact, a helium atom moving even at 4 electron volts can't quite make it through that hole. The threshold for getting through is a little bit higher than that. Here space is divided in two volumes with the thinnest of all possible membranes, and it turns out there's only one element that can make such a membrane all by itself, and it is carbon. And it has this wonderful property of being chemically robust in its, when you expose it to the other objects around, water, air, moisture, and most other things. That's really quite stunning when you realize how difficult it is to do this with any other element of the periodic table. And also when you realize, if you think of chemistry or material science as an exercise in architecture, engineering things on a nanometer scale, when you realize how important it is to have low-dimensional building blocks, 1 and 2 dimensional building blocks with which to construct interesting architectures in 3 dimensions. We need to have a 2-dimensional surface at 1 atom wide thick with which to build things, and the good Lord has given it to us in the graphene sheet. And it turns out that in order to provide the positive curvature necessary to make the end caps here, or the negative curvature to make these little bits, the pentagons and the heptagons actually don't cost that much in energy to put in, so that it's actually a functional engineering strategy for constructing structures. And as you think about it, it turns out there is truly an infinity of possible structures here. You can make a single fullerene to conform to any topology that we know of in 3-dimensional space. And one of these days, we'll probably figure out how to make pretty well anything we can imagine. But rather than talking about all the sort of funky fullerenes that one can imagine, we're going to talk about just one. A direct linear extension of the fullerene idea along one direction. It is an extension for which the first step is C70 already, which is C60 cut at the equator, the two halves rotated a bit, a new added ring of hexagons put around, of carbon atoms put around the center to make this elongated object. This is, in a sense, the first Bucky tube. It's getting longer in one dimension. It still has this property that as a molecule still divides space into two equal volumes. If instead of putting one ring of carbons there, we had put instead a whole stack of, say, 100 rings, and then the two end caps, we would have, again, a molecule, a capsule, a fullerene capsule. And if, while we're dreaming, instead of putting 100 rings together before we put the end caps, let's suppose we put 1,000,000. And then put an end cap way over there on that end, one here. It's so long I can't hold the two end caps in my hand, so the hell with them, we won't even think about them. Just grab it by the side. This tube, which is just the old graphene sheet wrapped around and sealed seamlessly on itself. It's an incredible object. Because if you pull the tube and you ask the question, how much force per cross-sectional area do I have to put on it before it breaks? The answer looks as that it's going to be roughly 100 times stronger than steel. And in fact, if you then ask the question, well, is there any other object I could hold in my hands made of any combination of elements in the periodic table with any sort of strategy that would be stronger than that? The answer, it looks like now, is no. This is it. It's the strongest fiber you will ever make out of anything, any kind, made out of carbon. Now, it turns out that that tube of this diameter is pretty highly stressed. If you take the graphene sheet and you wrap it around this diameter cylinder, which is 7/10 of a nanometer diameter of the cylinder that has the nuclei, or almost precisely 1 nanometer diameter at the van der Waals distance on that side, the energy to stress the graphene sheet around that cylinder is rather significant, and it is not the one that nature likes to make the best. Nature likes to make a tube that is precisely twice that diameter, and it is this one. These things are inevitably called with the Bucky prefix name, which has now become the generic prefix of this business. This is a Bucky tube, and it's a particular one. It is one that is the most favored in a formation mechanism that I will talk about in a bit, where these things are formed just in the same way that buckyballs are formed, by carbon condensing out of inert gas at a moderate temperature. Let me point out that a few details. If you look at the end of this tube, if you cut it open with a cut that's precisely perpendicular to the tube axis, you notice that only the sides of the hexagons are exposed. This is generally called the armchair edge. I guess that's the arm of the armchair, and this is the seat of the armchair, and so there's enough place for 10 people to sit on this. One of the properties of these armchair tubes is that if you calculate the band structure of the tube, and I'll show you such a calculation in a minute, you find out that even though this is carbon, in the same structure that we're familiar with in graphite, unlike graphite, which is a single graphene sheet is a zero-gap semiconductor, and graphite itself is a semi-metal with a very slight overlap. This sucker is a metal. There are two bands that cross the Fermi energy at 2/3 of the way across the Goldilocks zone, and is forced to do that by symmetry. So this, as we'll see in a bit, as you've probably heard, turns out in fact to be a quantum wire. This particular tube has the property that the inside, the hole down the inside, is precisely the right diameter to put a buckyball or C70 on the inside. It's actually kind of spooky that turns out to be the case. The end cap that goes to this 1010 tube, is the one that is most energetically favored, is half of C240. C240, its most energetically favored form, is a round buckyball shape with the pentagons, all 12 of them, separated apart from one another as far as they can possibly be, and that's done with perfect icosahedral symmetry. It turns out to be the next fullerene up from C60 that has perfect icosahedral symmetry and has the same relationship between the pentagons, namely to get from one pentagon to another, you go to a vertex and follow along the bond and you'll find the next pentagon. C240 is the next member up of that family. It still strikes me as very suspicious and spooky that C60 fits precisely inside the C240. The distance between the outside surface of C60 and the inside surface of C240 is precisely the same number, 1 nanometer. This is a canonical 1 nanometer, God's measurement of 1 nanometer. One wonders how the French figured out the meter from this. In any event, this tube, which for fascinating reasons turns out to be the one that grows so preferentially in the gas station, happens to be the one whose end cap has half of C240, which means a buckyball, or C70, which has its end cap being the same as the buckyball, conforms to the inside surface of this perfectly and would slide along the tube like a BB. It's not clear yet quite what the good Lord had in mind with this when he started the universe, but we could probably make some gadgetry starting with that. If I might get to that, one of the ideas is to make a little memory which has a fullerene capsule and a buckyball inside that shuttles back and forth. It's bit is 0 over here, is 1 over there. It's called the Bucky shuttle memory. It turns out that we've just found within the past few years that this sort of material can be made really quite straightforwardly just by vaporizing carbon and letting it condense with a catalyst. Actually, the first time this was seen was back in 1993 by 2 groups. One, Sumio Ojima at NEC. Sumio is here in the audience someplace over here. And almost simultaneously by Don Bethune and his group at IBM and Almaden Labs near San Jose. They published back-to-back papers in Nature showing for the first time single-walled nanotubes of about the diameter of this 1010 tube. In Dr. Ojima's work, it was done by arcing 2 electrodes, carbon electrodes together in a methane atmosphere, an inert atmosphere that had about, what, 10 torr methane, was it? 50 torr or something like that? 1,200 torr? 500 torr. With iron, a little bit of iron particles in the anode. And in the IBM Bethune work, it was carbon electrodes with cobalt in the anode in an inert environment. And both of them saw these single-wall nanotubes in small amounts. We got into this game a while back trying to figure out what the mechanism for the growth of that was, and it occurred to me that the mechanism might have a lot to do with the way the buckyballs are made. So we went into an environment which, if you just have a pure carbon target and you hit it with a laser, you collect the material that forms back here, you find that 30 to 40% of all the carbon that's vaporized condenses to form C60 and the other small spheroidal fullerenes. And we mixed in some cobalt, and by this time it was known that alloys are good for these catalysts. Cobalt and nickel catalyst within the carbon pressed pellet, and then at 1200 degrees vaporized this with lasers. And we were stunned to find that not only were there single-wall nanotubes there, but there was at least 60% of all the material that condensed that formed in these nanotubes, and we subsequently perfected the method. So on our good days, when we collect the stuff back here, 90% of all the stuff that is there is tubes. And if you just take some of this raw stuff and look at it with an electron microscope, you see just tangles of carbon fibers. And these fibers here that you see in this raw material, we call it a felt, are actually not individual nanotubes, but rather they are constructed of hundreds of individual tubes. I'm looking for, here we go. So if you look at the side of one of these fibers, you'll find that there consists of, in this case, well over 100 individual tubes. You can see them along the side of the rope here, or what appears to be the end, but this is really a rope of these carbon tubes bending through the field of view of the transmission electron microscope. And you notice these tubes are arrayed here in a rather crystalline lattice. You notice these lattice plates going through here, and they all seem to be about the same diameters. And it turns out that they are very close to being the same diameter, and there is one tube that appears to be present more than other tubes, and it is in fact this one called a 1010 tube, which has this remarkable band structure. This is the energy of the electronic bands as a function of the wave vector, or the electronic wave function going down the tube. And here are these two bands that cross the Fermi energy here, right in the middle of the Fermi energy. It guarantees this sucker is a true metal. And in wondering why this tube would be formed, we have conjured up a mechanism for its formation, which we gave a cute little title, the Scooter mechanism. I don't have enough time to talk about it, except to say that what we think is going on here is very much what goes on when buckyballs themselves form. Namely, you make a carbon vapor, it starts to condense, you start to get a little carbon network, mostly hexagons, a little raft growing in the gas phase, but there's all these dangling bonds on the periphery of the raft, and those are tremendously high energy for carbon. And so if the temperature is high enough that this raft can wriggle around and rearrange its bonding to try to minimize this edge area, it will do that. There's two strategies that it can use. One is it can rearrange so that there are pentagons in the structure. That gives it this positive curvature that allows it to reduce the peripheral circumference energy of this high energy edge. And the other is it can rearrange the positions of the pentagons so that at that exposed edge, you only have sides of polygons, not vertices. When you have the sides of the polygon, then there are always the carbon edge atoms always come in pairs, and you can form a fairly good, it turns out, triple bond with those edges. So that formally, if you could do it right all the way around the edge, there are no dangling bonds at all. There are just sort of mediocre triple bonds. Well, it turns out that the pattern of pentagons that does that and maintains it as you curve around is precisely the pattern of pentagons that will give you C60. And that's the reason we think that C60 forms in such high yield, is that kinetically there is a path, which is the lowest energy path that goes there. If you don't quite do it perfectly, you'll make some other full ring before it closes off. Well, we think that these tubes are basically a detour off of that path. And this thing starts growing and starts curving and rearranging to drop its edge energy, but now there's condensing in the carbon vapor some metal atoms, nickel or cobalt. And if one or two of these hit the side of it, move around, it's certainly going to bind on that open edge much more strongly than on the surface. And what will that do? Well, we know that nickel and cobalt and iron and these other atoms are extremely good at catalyzing the rearrangement of carbon networks, particularly aromatic carbon. And that's all we think this little drug does. It goes scooting around. It doesn't have to be just one, but one is probably enough in many cases. If it is able to move around any time it encounters something that isn't a hexagon, which is locally going to be a higher energy structure, it eases its kinetic path to become a hexagon. as long as it can keep moving around, scooting around the edge, it keeps any pentagons in particular from forming. And if you can't make any pentagons, this thing will be a tube forever. And then the theory goes on that, well, if the temperature's hot enough and there's enough time, this little tublet, which has 1 or 2 or 3 metal atoms on the end covering and keeping it open, if the temperature's high enough that it can relax and rearrange to the most energetically favored tublet, there will be one tube that will be most favored. And we believe, and the calculations confirm, that that should be the 1010 tublet. And if it isn't 1010, it should be a tube that's close to that in diameter. And if it isn't perfectly this armchair edge, which allows you to make triple bonds all around that edge and lower the edge energy, it'll be something that's close to that. Just a few exceptions to just the size. And that seems to be consistent with what's seen. We know that this material actually conducts electricity, as you'd expect for something that's metallic. This material forms in a felt that you can pick up with your fingers and pull on it. It's really good stuff. It kind of screeches back at you. It kind of goes, you pull on it. And you can actually go in and drag out one of these ropes and make a measurement on it. And this is a picture of this being done. And here's a piece of this felt that's actually held in a little alligator clip. And over here we have a platinum needle that's been electrochemically sharpened. And we first stick that needle in a couple microns into the stickum on Scotch tape and then pull it back out. Put a little stickum on the end of the needle, and then we shove it into the felt and pull it back out, and usually one of these ropes in the felt will get tangled in that glue, and as we pull it out, it will ultimately starts pulling the felt tangle behind it. And you can't actually quite see this rope here, but you know it's there because as you pull the needle, it follows it up and down. And here we have actually brought in 2 other electrodes. These are actually multi-volt nanotubes to measure the voltage drop across this rope as we run current between these 2 things. And with this, we can measure the resistivity. Well, really, actually, it's an upper limit of the resistivity. And it turns out that it's a little bit better than perfect in-plane graphite for this particular rope. Actually, we used this scheme in the groundbreaking ceremony of the new nano building at Rice. It was a sort of a ribbon cutting ceremony. Except in this case, it was a nano ribbon. It was the first nano ribbon cutting ceremony anybody had attended where they couldn't actually quite see the ribbon they cut. But we got this done actually in real time, and then we sent a major current between these 2 points and broke this like a fuse, and that was the signal to set off a little explosion that actually broke ground in this building. More careful measurements of the resistance of these things is being done now. It turns out that the temperature dependence of the resistivity of these metallic tubes is by and large linear over very large regions of temperature. This goes from room temperature down to absolute 0, and it's linear down here until about 50 degrees Kelvin. We know that these same materials continue being linear with the same, actually fairly slow slope, all the way up to 1200 degrees centigrade. This slope is quite small. Here at 300, we're at, 1150 degrees ohms, and down here at absolute 0 extrapolates to only a couple hundred ohms less resistance. So there's only a couple 10-20% increase in the resistance going all the way up from absolute 0 room temperature, and that slope stays the constant all the way going up to 1200. So extremely slow variation in the resistance with temperature. There have been some beautiful experiments done recently in Holland and in California and Berkeley on quantum transport of individual ones. One of these done by Case Decker and his crew. Case is here in the audience someplace. Case is over here, on the cover of Nature, which very nicely showed that the transport along this wire involves coherent states that appear to be coherent over the whole length of this molecular molecular wire, actually for distances considerably longer than you see here, on the order of 3 microns in length. That there are basically particle in a box states in these essentially linear tubes, which are just what you calculate for a particle in a 3 micron box, and those are the levels that are being total here. I kind of like this because you look at this picture, and there's this beautiful blue thing here, and there's this ugly, bumpy old stuff up here. This is actually platinum, isn't it? It's not, although it looks like gold. And say, oh, what a yucky technology. But this is actually very high technology. This is microlithography done at scale. This is only, what, about 100 nanometers across here. And this is on silicon, I believe, isn't it? Silicon oxide. And so this is the old yucky technology of microelectronics. And then here, casually draped across it, is the new technology. This is the way to make a wire, not this cruddy old stuff. This thing is a single molecule. It's actually considerably thinner than seen here. This is extra fattened by the tip that the Decker crew was using. So one of the intriguing aspects about this is we appear to have the answer of how to make a molecular wire. Make it just simply out of carbon. If you pick one of these armchair tubes, it's guaranteed to be metallic. And it appears to be metallic all the way down to, in this case, millikelvin degree temperatures. What happened to the Peierls instability of one-dimensional wires? Well, we're not quite sure, but we think it may have just up and gone away because this tube has such tremendous structural rigidity to it that the energy cost of making a distortion that would open up a gap in beryllium azote is greater than the energy advantage you would make by stabilizing a bit the otherwise conduction electrons. But in any event, the practical reality is that it appears to act like a waveguide for electrons. And because of its small size, it's guaranteed to have a propensity to like particular waveguide motions to it. But also, here we have effectively a single crystal wire with the most rigid lattice that's available. So symmetry dominates this thing. So the transport mode for electrons going on this wire is always one that has 10 radial nodes, 10 angular nodes, and 1 radial node in these 2 bands that cross. So a very particular waveguide mode. These tubes, as I say, are effectively single crystals of carbon in one direction. The unit cell of this tube is this thing that has 2 up and 2 down, going along that direction. In this tube, the point group symmetry of that unit cell, D10D, is sufficient that every atom is identical to every other one by symmetry. It shares with C60 this property. The symmetry is sufficient to completely determine the problem. It's quite a wonderful circumstance. As I mentioned, it does, in simulations, appear to be incredibly strong. There is an indication that we may be able to pull this tube before it fails to 20 to 30% elongation before it finally fails. And when it fails at even 30% elongation, it doesn't fail by brittle failure, but rather by plastic pulling on threads. That would give us a tensile strength something like 300 gigapascal or so. Easily the strongest fiber that had ever been made. So, that being the case, perhaps we, instead of thinking of this as a single crystal of carbon, we should think of it as a new polymer. It's made out of carbon. The monomer is either carbon atoms, or if you prefer to think of it, it's this ring of 40 carbon atoms around the unit cell. Tremendous tensile strength, electrical conductivity, maybe upwards and competitive with copper, for all we know might be better. Thermal conductivity, inherited from that of the graphene sheet and HOPG or crystalline graphite, may be rivaling that of diamond. This would be a tremendous engineering polymer if we were able to make this. So there is a great interest now in trying to figure out how to make these fibers continuously and how to do it cheaply enough to make it of economic, ecological significance. Is there any chance of doing it? If you're going to do it with lasers, forget it. It just costs too much energy to make the laser photon, too much money to make the laser photon, for you ever to make this stuff by the ton practically. Even if any way you vaporize carbon, the temperatures required are so high that you're never going to make this by the megaton if you have carbon vapors being the feedstock. The only way to make it by the megaton economically is to make it from hydrocarbons. Is there a way? And yes, we think there almost certainly is a way. The catalyst already on the end of these growing tubes, we know what it is. It's a little cluster of nickel and cobalt. I mean, I said there was one little scooter atom initially back in nucleation, but after it's nucleated and starts to grow, other atoms aggregate, and we know that after a while a little cluster sits there. Well, we know the property of that cluster. Nickel and cobalt doesn't have to be nickel or cobalt. There's a wide range of transition metals that are active. If you take such a metal cluster at a temperature anywhere near 1,000 degrees centigrade, then you expose any hydrocarbon to it. They'll just rip it apart. So ethylene, for example, if it comes up to this thing, will dissociatively chemabsorb. The hydrogens will go off at these temperatures H2, driven by the entropy of H2 in the gas phase, leaving carbons behind on the surface. Without enough hydrogens to form a volatile molecule, they're sunk. They have no place else to go. They got to stay there. And it turns out that these transition metals at these temperatures are effectively solvents for carbon. They're solvents for carbon, just like water is a solvent for sugar. And we're growing a single crystal, and the way you grow single crystals of sugar is you put a seed crystal in, you do things carefully so that no other nucleation event happens, and then those sugar molecules will work their way down onto this crystal, and off you go to the races. Well, we already have the seed crystals. We're playing with them now. We already have the catalyst. All we have to do is hold this sucker out, feed it hydrocarbon, and we'll get rich. Now, it's easy to do this on the picture, but this is only the diameter of the DNA double helix here. And I haven't figured out yet how to hold that thing out there. You might go home tonight and think about that. It's potentially could grow quite rapidly and maintain its perfection because it's only a nanometer from here to there. And one of the difficulties in crystal growth is you have to make sure that there's enough time for bad things to get unbad and the feedstock to diffuse over to some place that can be good. And so diffusion is a problem. Well, diffusion has this terrible problem that if you go to longer distances, it takes much longer in time for the square. But if you turn that problem in reverse, when you get smaller, things get much better and much quicker. 1 nanometer makes diffusion not a problem at all. So this thing has a chance of growing with great perfection at high velocities. So it isn't at all inconceivable that you might find that in 5, 10, 15 years there are huge plants producing carbon fibers in aligned single threads, cables, random fibers. And that the product of those plants is shipped out in ships, not even in 55-gallon drums, but really huge megatons per year production. Well, if you can do that, then it turns out, and I'll stop with this, you can do this. You can build an elevator in space. You may know of this science fiction lovely book, Fountains of Paradise by Arthur Clarke. He's one of the principal proponents of this. And the notion here is that you go to some hardware store in the future and you buy a fishing line and a big long length of it, and then you go down to Johnson Kennedy Space Center and you put it in a satellite and you ship the satellite up to synchronous orbit. And you get up there and open a little door in the bottom, and you take a piece of the end of the fishing line, you tie it to a little lead weight, and you throw it out the bottom of the satellite. You got to throw it initially. And after a while, it starts tugging on you. As you reel it out, it gets heavier and heavier and heavier. And with any fishing line that we have now, you can't quite make it all the way down to the surface of the earth. Actually, I don't think this is true. I think if you use this new fiber spectra, which is really polyethylene, you actually could make it all the way down to the surface of the earth. But anyway, it turns out that the strength that you need for something of the density of a Bucky cable, tensile strength, actually no, I guess you couldn't do this better. The tensile strength you need to get all the way down with a constant diameter, all the way down, and that's what, 36,000 kilometers down, is 63 gigapascals. The strongest steels are about 2. But the prediction for these Bucky fibers is hundreds of gigapascals. So it looks like even with a constant diameter, you could lower this down from space. And then, of course, you take this fiber when it gets down to the ground, your buddy's down there, and he grabs it, ties it to a tree, and just pulls on it to say, send more fiber, you know. It's interesting that it takes 4 hours for the speed of sound to send that impulse back up to the satellite. Then you finally get something about 1 inch diameter. At the tensile strength we're calculating, that would be worth about 50 million pounds that you could hold. We build a box around this, put a motor in the box, the door of the box, walk in, close it behind it, and go to the wall, push the button that says up, and you take an elevator to space. Of course, you wouldn't make just one going up, you'd have one coming down, trade energy back and forth. Luckily, these things are electrical conductors, there's no problem with that. Those of you who are interested in this fantasy, I recommend you see the July-August issue this year. American scientist Boris Jakobson has done a beautiful job in preparing this article that summarizes this crazy future of the carbon. It's really just what we've always been doing, but this is the incredible thing to be if you can actually construct a macroscopic object where the carbon is all nanoscopically, molecularly perfect. Thank you for your attention.
Will you entertain the question?
Sure.
Anybody would like to ask a question, please stand up.
You're such an incredible optimist about the future. I wonder if
Incredible, that means not credible.
I didn't mean that. But I wondered, through your career, did you always have this outlook prior to your Nobel Prize? Or
Yeah, I've always been crazy. I've been talking about this for years now. And never in the past have we managed to make this carbon fiber, so one could be skeptical. But I find this argument to be very compelling. That we have this seed crystal already. We know this catalyst. This is not a ribosome. This is nothing very subtle about that catalyst. It's really, in this case, just acting as a solvent, and also double pitch hits as a gas phase, a converter of gas phase feedstock to the condenser. The most compelling aspect is that we know the energy happiness, the thermodynamic happiness of these atoms in this tube. And after all, they're in a perfect hexagonal network. The only reason this carbon atom here is not as happy as it would be in the most stable possible form of carbon available at this pressure, perfect graphite, is the fact that sheet has been wrapped over this cylinder. And we know precisely the energy cost of that. It's only 48 millivolts. That's only 0.6% of the cohesive energy of a carbon in the perfect graphite. So these carbon atoms have 99.4% of the energy they're ever going to get in the most perfect infinite structure of graphite. Think of any other structure on a nanometer or 10 nanometer or even a micron scale. that has that property. There isn't, unless it's a larger diameter perfect tube. We take that too. So this is the deepest thermodynamic sink there exists for atoms in this world, in that little region. So that is the reason it makes me think there's got to be some way of doing this.
Curious if these buckyballs exhibit melting points like metals and like polymers, if they have any solvents.
Buckyballs don't melt. They sublime. There may be a molten range for them, but it's not one that anyone's ever established yet. I think most of this is because they're already spinning randomly. They don't have much entropy advantage of going into a liquid. We're very interested in the question of the bucky tubes in these ropes, whether we can get them to melt and get the individual tubes to move off. So far they do in simulations and computers, but it's not quite clear they do it in the laboratory. You were asking about solvents?
Yes, if the bucky tubes have any solvents. Yeah.
We're working now extensively in my group purifying these random carbon fibers and cutting them so that we get short lengths. The purification involves cooking them in oxidizing acids. And whether it's an intrinsic part of the tube or it's part of the goo that's highly oxidized that we make with the tubes, the end result is they suspend very well in the water, negatively charged. They're colloids in a way. And the cut pieces are colloids too. But we don't know yet enough about it. I don't think we really have the pure stuff yet. So I don't know what the answer to the question is. I'm looking for a slide here because I want to make one little point. Well, I guess I could make it with this one. It's not quite what I'm looking for. Rather than thinking about infinite long cables to Mars and getting rich as sin by founding $1 billion new polymer industry, think about the individual pieces of tubes. I haven't got this one cut, but I have an image one. Suppose I just went in here and I took one of these things, I cut it, held it in my hands. And that entity is a molecule. And the cut edge, I can derivatize those dangling bonds with essentially any organic substitute I want. I can attach essentially any molecule, enzyme, membrane, surface I want to this surface with good covalent bonds. It's actually 20 to 40 different places I could do it on this end. On the closed cap over here, with the bonds that radiate out from the pentagons, there's addition chemistry that works there. It's the chemistry of fullerenes. And once again, I can attach any molecule, enzyme, surface, membrane I want to this end. And the end result is a molecule, perfectly happy to be around in the real world with air and moisture around. But this entity over here, let's call it A, and this one over here, let's call it B, are connected by this tube, not only mechanically, but for the first time in a way that should be able to do this with air and moisture around. They're connected by true metallic transport between these two things. We have never really had that option before in molecules. We've had conducting molecules, but they're frankly not very good conductors compared to gold. Or if we dope them, they get to be good conductors, but then they're terrible molecules. They can't survive in the real world. Here in this nanotube, we appear to have both. We have a truly metallic transport down a graphene tube, which is chemically very happy to be in the real world, but it's metallic. A true coherent transport. And so here's a whole new branch of organic chemistry, which now has electricity as part of its game. Conceivably, there could be a branch of organic chemistry where instead of the people in that discipline going out and getting jobs to make pharmaceuticals or polymers, paints and so forth. They make devices, electrical devices. Actually, this slide is meant to talk about a whole different aspect, which is to use these tubes as nano fingers and probes of the nanometer world. There's a whole line of thinking here that in many ways is equally, if not even more exciting than these other stuff I'm talking about.
Now we've got this beautiful object which has tremendous possibilities, and now we can see it has a great possibility of being produced. I happen to be a computer scientist, and we have the notion of the killer application.
Killer app.
So what's the killer application?
Maybe lithium batteries. The raw felts right now are very interesting, particularly when you purify them, because you have all this surface area. It's very accessible. And the tubes are, well, at least many of them are metallic. And they're also, we suspect, excellent thermal conductors. Even just the raw stuff is interesting to consider as the anode in the lithium-ion battery. But if you really get down to the point where we can control this stuff, we can fabricate membranes, where the membrane is a bed of nails. So the tubes are going in the perpendicular direction of the membrane. You turn the membrane up this way, you'll see through the tubes. So this membrane could actually be pretty thick, and there's nice places for the lithium ions to go in between the tubes, in a little triangular gap, and if we cut the ends of the tubes off, and I promise you we know how to do this now, there's the little channel down the middle, and they're made out of carbon. So if you don't like those tubes, you can derivatize them. So here is the possibility of engineering membranes on a length scale with precision that we never thought possible before. I don't know what the killer app is. For tubes, it's possible to get pretty excited about a lot of possible technological applications. That the level of interest gets much higher than it ever got with the carbon bulb. But it might very well be true that we're still 10 years away from being able to make it and control it well enough and identify the killer app that really turns it on.
I have a sort of a technical question here. The talented people have been making these fibers for many years by decomposing hydrocarbons on particles. What's the difference between those structures and the structures you're describing here?
That process is basically the same one I'm talking about. It's just that here you're at the limit of perfection of that process. Or some of the think of these things as fibers, this is the limit of the evolution of graphite fibers. If you look at the history of graphite fibers, it's been a series of small, minor revolutions, where at each stage the fiber has had the graphene sheets more aligned along the axis. But this is the end point. And rather than using 2,000 to 3,000 degrees centigrade to do it, you use a catalyst and you make a molecule. And it keeps on being perfect because the only place there's a very active edge is right at that lip. And thermodynamically, what you want to make is so much better than anything else that that's what's made. But yeah, this is the same deal. It's a question of how you nucleate it.
Does it have to be a carbon atom as the radical, or could it be some other radical?
Any source of carbon, I think, is good enough. So it could be carbon vapor, it could be hydrocarbons, it could be carbon monoxide. At 1,000 degrees centigrade, all God's children pyrolyze and we do graphite and hydrogen, right? If there's any other atoms around, you'll make water or CO or H2S. So this is, we're not trying to make DNA here.
I wanted to ask about the elevator. I didn't try to understand who is going to fit inside the mountain.
Oh, no, not inside the tube. Only buckyballs can fit inside the tube.
It's a buckyball?
What?
It use the elevator for buckyballs?
It would be an elevator. We can vent the excess buckyball population on the earth.
So I think to stay on schedule, we should thank Professor Smalley and proceed back to the meeting rooms.